All right, so in this video, we're going to be looking at how to convert systems of equations into matrices or matrix equations that we can then do various linear algebra processes on. So let's consider a system of equations. In this case, we're looking at three variables. We have 3x minus y plus z is 6, 4x plus y minus z is equal to 8, and negative 2x minus 3y plus z is equal to 10. So one way that we can work with this system of equation as a matrix is to convert it to an augmented matrix. So in this type of matrix, we're going to essentially make each column represent a single variable, and then the final column will represent the set of constants that are the solutions to the equations, or the constants inside of our equation. So if any variables are missing, replace them with a 0 in that position. So here we'll have 3x just becomes a 3 because the first column is representing our coefficients for x. And then the second position becomes minus 1 because the sign goes with the constant. And then z is just a coefficient of 1. And then the constant on the other side of the equation is a 6. Sometimes in augmented matrices, you will see a line separating the coefficients of the variables from the constants, but this is not universal. Sometimes it's just there in the beginning in order to remind you there is really two things going on in this matrix, but typically after a while, people will stop writing it. The second equation, the coefficient of x is 4. The coefficient of y is 1. Again, the negative goes with the coefficient, so this coefficient would be negative 1, and then here's our 8. And then x has a coefficient of negative 2, y negative 3, z is 1, and then the constant is 10. And so this would be our augmented matrix. We can then perform row operations on this, similar to what we were doing in a previous video. To solve for our inverse matrix, we would ideally want to be able to turn this side of the equation into an identity if possible. And then if we can do that, then this last column will be our solutions. X is equal to whatever this number is, y is equal to whatever this number turns out to be, z would be equal to whatever that turns out to be. But so that is an augmented form. We would do these row operations in order to solve the system. Now, we can also turn this into a matrix equation. A matrix equation is going to put the coefficients from the left side of our equation into a matrix by itself. We're going to multiply by a vector that contains the variable names, x, y, z in this case, or x1, x2, and x3, if you're in linear algebra typically. And then on the other side of your equality would be another vector that represents the constants from your system, 6, 8, and 10. This is the kind of system version that you would want if you want to use an inverse. For this kind of a problem, you would multiply on both sides of your equation on the left by the inverse of your coefficient matrix, and then your x, y, and z will be the solutions that you get from doing that multiplication on the right side of the equation. Now, there is also one other version that you can create for systems of equations like this, is a vector form of the equation. In that case, what you would essentially have is this first column vector would be multiplied by the variable x, and then the second column would be multiplied by the variable y, and then the third column would be multiplied by the variable z, and then on the other side of the equation, you would still have your vector 6, 8, 10. That doesn't help us with matrix operations, but it is another way of thinking about our system of equations in terms of vectors, and so it can be a very important interpretation problem in terms of how we're representing our solution as linear combinations of these column vectors from our coefficient matrix. So it is an important version of the equation, but it's not strictly a matrix thing. It's more a vector thing. And so we don't have an example of it here. In the next video, we're going to talk about strategies for solving systems of equations once we have them, once we have our system of equation in the proper form.